Hello, everyone. We'll give people a couple more seconds to join in and then get started. Okay. Good afternoon. I'm Karina Smetny with CAI, and welcome to session 27 with Dr. Niexila and Dr. Hayovsky. We're very excited to have you here today. Before we get started, for the last time, just a couple more reminders for a smooth session. We will be monitoring the chat, so please feel free to use that for comments and questions in Whova, not Zoom. And the speakers will take your questions after the last 10 minutes of the session. All of these sessions are being recorded and will be available on demand after the conference. We will send out an email to all attendees when each is available. Handouts are in Whova under the session. If you cannot access the handouts, please email us at caipsychs@gmail.com. The survey and quizzes are located in each session description and may be complete at the conclusion of the session that you will need for CEs. You can also open it up another time in another window when you have time. This session has been sponsored by Riverside Insights. We would like to give them a few minutes to say a few words. So Amanda, I will pass it on over to you. Thank you.
Awesome. Thank you, Karina. Riverside Insights is proud to support the 2025 CAI conference. I know I personally have really enjoyed the first day and now the second day of sessions, and I hope you all enjoyed them as well. We'd like to remind you that WJ5 launches on February 1st. We're very excited about that. There's a lot of cool information about the new tests, new features, and everything that's coming soon. So please visit our website for the latest information there. And I'm looking forward to a final finale session. So thanks, everyone.
Thank you very much, Amanda, and thank you, Riverside, for co-sponsoring the conference. It has been tremendous, and we are coming to the final session here. And while our presenters may be last, I can assure you they are not the least. I had the good fortune of moderating their session last year, and I learned a great deal, and I'm very much looking forward to their presentation this year, which I assure you will be high quality as well, judging from the design quality of their initial slide, as you can see. Let me introduce them. All right. We'll start with Dr. Christopher Niexila. He is an associate professor in the Department of Educational Psychology, University of Kansas. He's also a licensed psychologist and a training director for the School Psychology Doctoral Program. He teaches courses in school psychology and for the school psychology program. His research interests are related to measurement invariance, longitudinal methods for examining predictors and processes of change in academic, cognitive, and social emotional skills, and the evaluation and identification of specific learning disabilities. Welcome, Dr. Niexila. Alongside, it's his, I guess, partner in crime here, because I never see them apart. However, Dr. Daniel Hayovsky is associate professor and associate department head in the Department of Educational Psychology at Texas A&M University. He's a faculty member in the school psychology program, where he also serves as chair and director of clinical training of the APA accredited program. Dr. Hayovsky is a licensed psychologist and nationally certified school psychologist. Most of his clinical work is focused on evaluations for children and adults with learning disabilities and ADHD. His research interests are generally in the areas of assessment and measurement, and specifically the assessment of academic and cognitive abilities, identification of specific learning disabilities, and the longitudinal development of psychological and contextual factors that affect academic, social, and behavioral skills. He is the deputy editor for the Journal of School Psychology and an associate editor for the Journal of Psychoeducational Assessment. Gentlemen, it is my pleasure and privilege to welcome you to the conference, thanking you for your time and lending your expertise. And I'm going to turn it over to both of you, and you are all set to go. I will, by the way, monitor questions for you in the Whova chat. I will pass them on to you at the end of your session for the last 10 minutes of your session during the Q&A. So you won't need to worry about this. Otherwise, it's all yours.
All right, great. Well, thank you, Dr. Ortiz, and thank you everybody for joining us today for the last session here. So today, Danny and I are going to be talking about cognitive achievement relations with the WJ5. So just before we get started and talk a little bit about what this presentation will be about, we just wanted to put out some acknowledgments there. So first, we want to thank Riverside Insights for access to the WJ5 normative sample data so we could conduct this research. It's always exciting when when a test is being revised and it's going to be coming out, and especially with the WJ because they always have really high quality normative samples. So the fact that we were able to work with this data before the test is even released in about a week or so was really exciting for us. So we really appreciate that. We also want to just thank CAI for inviting us to present our research at this conference. We presented last year. We really enjoyed it. And we were honored to be asked again to come in and present. And last, we want to thank everybody here for attending this presentation, the last session on the last day of the conference, and on a Friday afternoon, no less. So we really appreciate it. We're glad that you're here, and we hope that we're able to just give you some information and some new research findings that are interesting and exciting that'll be relevant for the WJ5. Just quickly, what we'll be doing today. This is the summary for the presentation. What we're going to be doing is talking about some research that we did where we're showing what the relationships are between cognitive abilities and academic skills using the standardization data for the WJ5. So what we're basically doing in this presentation is we're replicating some other research that's been done. So we're using similar methods, but we're doing it with the WJ5 that has a new sample and some new tests. And we really hope that this provides some more insights into understanding how academic skills develop, and then how that can be applied also to the identification of specific learning disabilities when we're thinking about identification from like a pattern of strengths and weaknesses type model. So that's our main summary. Just a quick overview. We're going to do some presenting on just some of the background and rationale for why cognitive achievement relations research is important, what it is, and what it kind of does and does not tell us about learning disabilities. Then we're going to review some of the previous research on cognitive achievement relations. We'll present the current study. We'll go through the methods that we used and then the results for reading, writing, and math. And we have results sort of like just across the whole lifespan. So from I think about age 6 through age 80. And then we'll end talking about some implications for research and practice, future directions, and then we'll have it open up for any questions or comments that folks have. So as far as the learning objectives for this presentation, one is to just review cognitive achievement relations research and how it's helped with the understanding of and identification of specific learning disability. The second one is to review the results and analyses of cognitive achievement relations with the WJ5. And our last one is that we want to provide some recommendations to researchers and practitioners on how this can be used with the WJ5 and maybe also inform some future research and practice. So with that, we're going to get into the background, and I'm going to turn control over to Danny, and I'm going to have him take over from here.
Okay, thank you, Chris. And again, good afternoon, everyone, and thank you for joining in on our presentation on a Friday afternoon. So to get in a little bit about the background on the purpose of conducting this type of research, we just want to showcase just some information here in terms of, what are cognitive achievement relations? Why are cognitive achievement relations important? How do cognitive achievement relations research specifically inform our understanding and assessment of a specific learning disability? And then finally, how do cognitive achievement relations research inform our actual practices for SLD identification? So in terms of, what are cognitive achievement relations? It's really a focus on the relationships between cognitive ability and academic achievement variables, and specifically looking at how do general intelligence and broad specific cognitive abilities influence different academic outcomes like reading, mathematics, and writing. Cognitive achievement relations research really examines whether cognitive abilities and how strongly cognitive abilities predict or influence different academic skills. Another thing about this type of research is it's moving beyond just a simple correlation between two variables and really looking at what we would put into a structural equation model, where we can model all these variables and their effects simultaneously. So again, it really looks beyond simple correlations between cognitive abilities and academic skills. When considering multiple cognitive abilities, like working memory, processing speed, comprehension, knowledge, and so on and so forth, when considering these multiple cognitive abilities, we really want to look at which ones explain unique variability or variance in the different academic skills that we're measuring. So as an example, let's say that working memory and verbal comprehension, they may have similar correlations with reading comprehension, but if we look at them as predictors of reading comprehension in the same model at the same time, one of the things we can answer is one a stronger predictor than the other? So for example, by including them all in the same model, we may find that verbal comprehension and working memory are both important, but verbal comprehension is relatively more important in explaining reading comprehension outcomes. So that's one of the benefits of doing this work within an SEM model. And then last, in terms of thinking about within the context, what are cognitive achievement relations? We're doing this work, conducting this analysis within the framework of what we call CHC theory, or Cattell-Horn-Carroll theory. CHC theory has really been a foundational framework that has driven this research over the past 3 decades. And what's nice and unique about the CHC taxonomy is that it really is helpful for categorizing what the different tests from different test batteries measure. Okay, in terms of why are cognitive achievement relations research important? Well, for one, if we know how cognitive abilities and academic skills are related, or how strongly they're related, we can really gather some fresh insight into why there may be individual differences in academic skills. So for example, people with strong performance in different specific cognitive abilities would be expected to have strong performance in academic skills. Another aspect is that if we know cognitive abilities and academic skills are related, we can really gather insight into how these things are related across time or across development. So a lot of the studies, including studies that Chris and I have conducted, we looked at both cross-sectional studies as well as longitudinal studies. Cross-sectional studies can be helpful in terms of a lot of the standardization sample data that we collect are often cross-sectional in nature. What's unique about a longitudinal study where they're sampling cognitive ability on the same individual over time is that you can really follow that same child or adolescent through development. And so you can really get some kind of unique patterns there as well. But conducting this research, whether it be cross-sectional or longitudinal, really helps inform our understanding of how these cognitive abilities and academic skills are related over time. And then last, if we know how cognitive abilities and academic skills are related, we can certainly gather some insight into what types of intervention may be helpful for improving those academic skills that are at risk or that may be at a deficit. So for example, coming back to verbal comprehension, if verbal comprehension is strongly related to reading comprehension, which we know it is, then we may be able to improve someone's reading comprehension by focusing on the development of, for example, something like vocabulary skills. Okay, in terms of how do cognitive achievement relations research inform our actual understanding of specific learning disabilities? Well, if specific cognitive abilities are uniquely related to academic skills, then it is plausible that deficits in those specific cognitive abilities may hinder academic skill development, or at least contribute to that academic skill difficulty. But this understanding does depend on many assumptions. We've just listed a couple here. Some of the assumptions are, do the different tests that we're measuring, do they measure the cognitive ability similarly, or are they measuring them a little differently? Another aspect is that when we use different tests, do the tests represent the actual ability well, apart from other factors that may be captured in that test, such as motivation, conscientiousness, those sorts of things. So are we adequately capturing that ability, or are we measuring the ability in some other thing like executive functioning? So it's really important to be able to tease those pieces apart when conducting cognitive achievement relations research. And then lastly, this is a really important point here. If a cognitive deficit plays what we call a causal role in an achievement deficit, then the observation of co-occurring achievement and cognitive deficits fit into this type of model. What do we mean when we say cause? We really like to think of this aspect that if you have a cognitive deficit, we can't know for certain that it causes an academic deficit, but we like to conceptualize it that if you have a cognitive deficit, it may raise the risk or increase the probability of developing an academic deficit. If we really wanted to get at, causality, we'd have to conduct a randomized control trial, which just isn't possible or ethical in these situations. But we can get a sense of how a cognitive deficit may increase the probability of developing an academic deficit. Okay, in terms of how do cognitive achievement relations research inform our actual practices of SLD identification? Well, one, research on cognitive achievement relations has been a foundation for SLD identification. If specific cognitive abilities are related to academic skills, which we know they are, then deficits in those abilities may indeed result in difficulties in learning those academic skills, or at least in those academic skills developing. Another aspect of this work is we look at, in cognitive achievement relations research, we look at general ability influences on academic outcomes, as well as specific cognitive ability influences on academic outcomes. When we're talking about an SLD, SLDs are assumed to occur in people who have generally average cognitive ability profile, rather than a mostly low average or low cognitive ability profile. So it's important to distinguish that when we're talking about an SLD, we're looking at cognitive ability influences on an academic outcome when most of those cognitive abilities we would say are intact or at least average, whereas maybe one or two may be at a deficit that could be contributing to that academic deficit. The other thing about cognitive achievement relations research is that it really nicely aligns with the SLD definition as operationalized in IDEIA, the Individuals with Disabilities Education Improvement Act. And in particular, the patterns of strengths and weaknesses models of SLD identification, they're really meant to help operationalize that IDEA definition of SLD. And those cog achievement relations really support this operationalization. Okay, in terms of just a little bit of research background on cognitive achievement relations, there have been mounds and mounds of work, we would say decades of work on this literature, and it's only continued to build up over time. Chris and I just finished a book chapter where we talk about the evolution of cognitive achievement relations research from the late 1990s, or I'm sorry, from the early 1990s until current era. And so we really kind of broke it down into kind of three segments. The first is from 1990 to 2010. And we're kind of calling this the past cognitive achievement relations research era. And during this time, there was really a major focus on how both general intelligence and specific abilities predict achievement. Again, general intelligence we think of as kind of the full-scale IQ, and we're talking about specific or broad abilities. We're really referring to those things like working memory, processing speed, comprehension, knowledge, so on and so forth. So again, it was really a focus on how both general and specific abilities predicted achievement. During this era, there was also a focus mostly on the statistical significance between cognitive ability and achievement, not so much on the size of that effect, but whether it was just simply statistically significant or not. And then last, even in the 1990s throughout 2010, there was a repeated finding that general intelligence was typically the strongest predictor of different academic outcomes like reading, writing, and math. And that still holds true today. Even in current research, we still find that general intelligence really explains the lion's share of the variance in different academic skills. But that's not to say that the specific abilities or the broad abilities still contribute unique and meaningful prediction to those academic outcomes. During this era, we also just want to highlight two big syntheses of cognitive achievement relations research that were published and that have been highly cited. The first was Flanagan et al. In 2006, and then the other shortly thereafter was by McGrew and Wendling in 2010. And these two studies really documented statistically significant relationships between cognitive abilities and mostly reading and mathematics outcomes. Most of the studies that were cited in these two syntheses relied mostly on WJ batteries, but these pieces of work did paint a clear picture of cog achievement relations that would not only be instrumental in developing PSW methods, but that would really be foundational to future cognitive achievement relations research. Again, during this era, there wasn't so much a quantification of the size of the relations between cognitive abilities and achievement, only whether really those relationships were statistically significant. So in this next era, we're going to see a bit of a shift, and we call this era from 2011 to 2024. And we call this the current cognitive achievement relations research era. And the big shift we saw here was one, that there was a bigger focus on effect sizes on between cognitive achievement relations. So for example, let's say comprehension knowledge has a statistically significant effect on reading comprehension. During this era, we started to ask, okay, it does, but was it a small, medium, or large effect as well? So we started to think in terms of those effect sizes more and more. Again, there's an increased emphasis on which abilities matter and how much they matter for different academic skills like reading, writing, and mathematics, and whether these effect sizes differed across age or grade level. And in the previous era that we just talked about, most of those cog-achieve relations were really between reading and mathematics. And we saw a further proliferation on studying writing achievement during this time. That work has picked up. So again, during this era, the focus shifted to which cognitive abilities were related to academic skills and how much those abilities were related to academic skills. There was also an extensive update to the literature base during this era, showing cognitive abilities predict reading, writing, and mathematics across the lifespan. So many studies that showed that cognitive abilities predicted achievement well beyond age 18. Another important piece to the puzzle during this era is that there was a bigger focus on what we call more integrated models of cognitive achievement relations research. So prior to this era, it was really just looking at how do cognitive abilities predict an academic outcome. The integrated model of cognitive achievement relations research era looked at how do cognitive abilities predict both intermediate academic skills and more advanced academic skills. So we'll show you what some of those models look like in a little bit, but it is just a quick example. Instead of just looking at how cognitive abilities predict reading comprehension, we started seeing models where cognitive abilities predict basic reading and reading comprehension, as well as basic reading predicting reading comprehension, all at the same time within one model. So that was really an important shift in some of this work as well. That's really advanced our understanding. Okay, so this next set of few slides here, this is really just kind of a broad overview of cognitive achievement relations research findings. And these are some of the select key studies that we cited here, but there's certainly several other studies out there that we didn't include. And again, this is just kind of a general overview. One of the things you're going to see pop up a lot is that comprehension knowledge tends to be important for almost every one of these academic skills. And when we think about comprehension knowledge, or GC, within the CHC nomenclature, we're really thinking comprehension knowledge in terms of a measure of background knowledge and language and vocabulary. And so much of our learning, especially early on, is language related. So it's not surprising to find that shows up quite a bit. But just kind of going through here briefly, when we think about basic reading skills, we see that comprehension knowledge, short-term memory, and processing speed have tended to be the most important across school-age children. And different authors here, including Chris and I, have looked at this. And the other thing that's notable about the different authors here, some of this work has been with the WJ, some has been with the KEBC, and I believe some has also been with the WISC. So it's a variety of test batteries where these findings have shown up. When we look at, reading fluency in terms of that reading speed and accuracy, there's been relatively less research overall when we can look at it compared to basic reading and reading comprehension, but we do still see that comprehension knowledge and processing speed do seem to be the most important. Again, you see some of the same authors popping up here. I know the Nilexila et al. 2016 was the WJ4 chapter, special validity study. And so in that sense, this study is kind of a comparison to that study. Cormier et al. In 2017 also found that fluid reasoning influenced reading fluency especially at the younger ages. When we look at reading comprehension or this ability to really extract meaning from text, again, we see that comprehension knowledge effects are important and they tend to increase with age. So in some of these findings, we see evidence of a developmental effect. As reading comprehension becomes more challenging or more demanding, we see something like comprehension knowledge, that broad ability, become increasingly important in explaining individual differences in that outcome. We also see different other broad ability, cognitive abilities like short-term memory, fluid reasoning, and processing speed to be related to reading comprehension. And again, with some of these articles, I know that for Floyd et al. 2012, Hayovsky 2014, and Alexa 2016, all of those studies use integrated models of cognitive achievement relations. So again, we're starting to see more of that proliferation of cognitive achievement relations research to advancing to the inclusion of more integrated models. So this is just kind of, again, a cursory or brief overview of the reading literature. When we look at mathematics, we really kind of break it down into math calculation versus math problem solving, as well as math fluency. And again, when thinking about math calculation, typically when we're thinking about that, the math problem is already set up for the individual, ready to be solved. It's really calling on, the understanding of those different procedural sets to be able to solve that math problem. Whereas when we think of math problem solving, we tend to think word problems. But the other piece about that is that in the math problem solving items, the problem isn't set up for the examinee. They have to develop an understanding of how to set the math problem up and then solve it. So there are some differences there in terms of what those look like. But again, what we see here is that comprehension knowledge, fluid reasoning, and processing speed, they all tend to be the most consistently related. Short-term memory may also influence both math calculation and math problem solving. And then some studies, it's a relatively rare, but we have also seen that some studies find visual processing to be related to math problem solving. And it would be interesting to look at, but I wonder if some of those findings may also be visual processing may be even more important for those who score much higher on the higher end of math problem solving when we think of a higher level physics or geometry. In terms of math fluency, again, fluency with those simple math operations like addition, subtraction, multiplication, again, quick but simple operations. It's not surprising to see that processing speed plays a seminal role. And this is even after controlling for math calculation skills in the model. And then also some other studies have found both processing speed and short-term memory to be important. Again, that's with Cameron and Alexa. So we see this across different studies, different samples, and different test batteries. Okay, and then last of the main three, reading, mathematics, and then writing. Again, we break this down into basic writing skills versus written expression. In basic writing skills, we think about a little bit more as that kind of mechanical aspect of writing. A lot of the spelling aspects that are involved as well. Whereas written expression, we're talking more about the aspect of being able to generate coherent written text and thinking about your audience when putting together that kind of written prose. So some differences there. But we do see with basic writing skills, comprehension knowledge, processing speed, and short-term memory, they all influence basic writing skills. So again, I believe every one of these domains, comprehension knowledge has shown up. Again, fluid reasoning, it may be important at different ages. So it's kind of just been some mixed findings there all the way back to 1993 up to 2016. In terms of written expression, so there were a few select studies like McGrew et al. In 93 where they looked at writing, but I saw more writing studies pick up kind of post 2010. But one of the things we find is that comprehension knowledge tends to be the most consistent influence, except in the WJ4. And we can get into later why that may be. But Floyd found that, I found that, Cormier and Alexa all have similar findings. We also found that processing speed influences written expression across different editions of the WJ. So whether we're talking about the WJ3, 4, and then of course we'll talk about our findings with the 5 today. Fluid reasoning and short-term memory effects, they're less consistent. So there's some mixed findings there across different batteries and different versions of the WJ. And then in some rare instances, in rare instances, visual spatial ability has been reported in 2 studies. So the Hayowski 2018 was with the KBC2 battery, and then I know the Nilexla 2016 was with the WJ4. So in those 2 studies, we actually found visual processing, or GV, to be important for written expression. Again, and we can talk a little bit later on about why that may have shown up. In terms of limitations of a lot of the previous research, one of the big reasons we talk about is that cognitive achievement relations research has largely been just based on, from one battery to another. So some of the findings may be just test specific. And really, what is promulgated by a lot of the different testing and evaluation standards agencies is that valid score interpretation, it really requires that construct relations generalize across different measures and are not test specific. And a little bit later on, Chris and I can talk about some of the work we're doing to kind of circumvent that limitation through meta SEM. Another limitation of a lot of the prior research is that there were just a handful of studies that focused on integrated models of achievement. Again, we're starting to see an increased proliferation of those type of studies. And so I think that's going to continue even more and more. We're even seeing insofar that and some of this work has been done where there's a greater use of network analysis models when thinking about cognitive achievement relations, and not only cognitive achievement, but cognitive basic academic skills and more advanced academic skills within one model. So I think that that's helpful to the literature. Another potential limitation of previous research is that we may not always be measuring the constructs well or consistently across different batteries. One of the issues that we butt up against is that many of the test batteries often only include 2 to 3 subtests measuring a broad construct. And we may not always be able to tap into that construct well or have good construct representation when we have fewer tests. And so what that can result in is not being able to adequately isolate what we call a broad ability versus a narrow ability. And just as one quick example, within the CHC taxonomy, I know typically we see, potentially over more than 15 broad abilities and over 80 different narrow abilities. But as an example of like comprehension knowledge being, one of the most commonly seen important broad abilities for explaining academic outcomes, some of the narrow abilities of GC include things like lexical development and general knowledge, for example. Those are 2 different narrow abilities of the overall broad ability comprehension knowledge. So as we measure these constructs better and better, and we include more tests, we can not only measure the broad ability well and how it influences academic outcomes, but we can also start to tap into those narrow abilities and how they influence academic outcomes as well. So that's a really important avenue of research. Again, some scholars have begun work to address some of these issues, namely Kammer in 2023 doing some of the kind of cross-battery cog-achieve research, as well as Matthew Reynolds in terms of doing the cross-battery work, looking at different test batteries. So that's been important. So I just previously mentioned meta SEM or metastructure equation modeling is one answer to help address some of the previous limitations. And there's actually been, several studies here already published. And these meta-analyses really examine correlations between individual broad cognitive abilities and academic skills. And what's really important about the meta-analysis, where it's different is in a typical study that's been done in the past, they're typically just working with a single test battery, a single sample, right? Whereas a meta-analysis really tries to aggregate and summarize the findings across all these individual studies. So it really helps control for differences in samples, test batteries, and whatnot. So it really gets you a more reliable picture of the relationship between a cognitive ability and an academic outcome. And so Pong Pong has contributed quite a bit to this body of research already. And so we just listed like the number of studies that he and his team has published on some of the stuff. So in 2015, they found correlations between math and working memory, which is also something that's been reported and even more recent research by others. In 2018, they found correlations between reading and working memory. In 2019, they found correlations between reading and math and fluid reasoning. And then in 2020, they found correlations between math and language. And so what's also important is that not only are these findings, they tend to be more reliable than a single study, but it also gives you a sense of the effect size. Are the relationships between math and this cognitive ability, are they considered small, moderate, or large, or even very large? And these meta-analyses can give us, more confidence that those effect sizes are accurate. In 2022, the authors also found that there were correlations between math and visual spatial processing. Again, Chris and I and several others, we're working on a meta-SEM of cog-achieve relations that hopefully we can talk about a little bit later that is similar to this to contribute to this body of work. A couple other pieces to mention in terms of looking when we're talking about the future of cog-achieve relations research. There were some other meta-analyses or research synthesis that we just want to mention here. Going back to McGrew and Windling when they published that in Psychology in the Schools. Again, that was a research review or a synthesis of the cog-achieve relations research. But again, in that work, there were no effect sizes calculated. They did talk about which relationships were statistically significant, but they didn't report as much in terms of the effect sizes. Zabowski et al. In 2018, they published in the Journal of School Psychology. They basically combined the effect sizes of cognitive achievement relations from previous studies. And then Bryan and Mayer, as recently as in 2020, they published in Intelligence. They examined relations among broad abilities, not specific to cognitive achievement relations. So they just looked at how strongly the relationships were between different broad abilities. So there has been some ongoing work in this area. And we anticipate that the future will continue to look at more kind of meta-structured equation modeling work to look at cognitive achievement relations research. And again, the benefit of that is that we're not just looking at a single test battery. We're able to combine multiple data sets at the same time when looking at these relationships. In terms of when thinking about correlated versus integrated models of achievement, something that we've been talking about a little bit here. Again, there has been some research where we've started using more integrated models of achievement, but it has been somewhat limited. So Floyd et al. 2012, I know they looked at an integrated model of reading where it included cognitive abilities, basic reading, and reading comprehension. I did the same here in 2014. Chris and Lexel and his authors did that with several different areas, reading, mathematics, and writing. And then Ethan Villeneuve and others in 2019 looked at an integrated model of mathematics. So how do cognitive abilities influence both math calculation, math problem solving, all simultaneously in one model? Again, that work is important to help broaden our understanding of cognitive achievement relations research. We do know that higher level reading, math, and writing skills, so higher level reading like reading comprehension, higher level math like math problem solving, and higher level writing skills like written expression, those areas are influenced by basic reading, math calculation, and basic writing skills. Again, those basic academic skills, they really serve as precursors to these more advanced skills. And so it's important for our models to conceptualize and estimate it in that manner. Again, integrated models of achievement, they really provide a more nuanced understanding of how cognitive abilities influence these more academic skills through more basic academic skills. So it really increases our understanding of how these things develop. And I think we may have a visual here to kind of give you an example here shortly. Correlated models, when thinking about correlated models versus integrated models, in correlated models, all academic skills are correlated with each other in the model. Cognitive abilities predict each academic skill. So for example, comprehension knowledge or GC, it's a statistically significant predictor of basic reading and reading comprehension, but the reading skills themselves are only correlated with each other. One is not predicting the other. And I think the visual on the next slide will help conceptualize that. In terms of an integrated model, we have multiple predictors. So for example, basic academic skills are predictor of the more complex academic skills like reading comprehension. So these models show how both basic academic skills predict complex academic skills. So again, just to break down this example, comprehension knowledge is a statistically significant predictor of both basic reading skills and reading comprehension. In addition to that, we can also model it where basic reading skills are also a statistically significant predictor of reading comprehension. So in this model, the relationship between GC and reading comprehension is partially explained by the relationship between GC and basic reading skills, and the relationship between basic reading skills and reading comprehension. So that's a mouthful, but I'd like to show you a visual here of what this may look like. So for example, on this model on the left here, we see a correlated achievement model. So here you see GC, which is our comprehension knowledge. We have GA as auditory processing, and then we have GWM as working memory. And we have these three broad cognitive abilities all simultaneously predicting both basic reading and reading comprehension. So in this model, basic reading and reading comprehension are correlated, but there's not a direct relationship from one to the other. So again, this is what a correlated achievement model looks like and how a lot of the past research had modeled this. When we look at a more integrated model of achievement, again, on the right here, same exact setup as the model on the left, but instead of basic reading and reading comp being just correlated, there's now a direct path. So in this model, basic reading has a direct effect on reading comprehension, which is this red arrow here. So a person's decoding ability has a direct influence on their reading comprehension ability, but part of the relationship between cognitive abilities and reading comprehension is explained by the relationships between cognitive abilities and basic reading. So for example, GC has a direct effect on reading comprehension, GC has a direct effect on basic reading, but GC also has an indirect effect of reading comprehension through its effect on basic reading. So we're able to get a much more nuanced understanding of how both basic and advanced academic skills develop in these models. Oh, okay. There's my red highlights. I missed those. I missed that on a click, but that kind of shows the different pathways. Okay, Chris, I'll pass it back over to you.
Right. And I'm gonna take away your control of my mouse here. Oh, here we go. 1 second. There we go. Yeah, because otherwise, if there's anything you're doing on your computer, it moves the mouse on my computer. So I'm going to get into the methods and results for the study. And so basically, when we have revised and updated norm reference tests, that's going to give us an opportunity to kind of look at things like cognitive achievement relations research with a new sample and with some new tests. So what's great about these norm reference tests is that they usually use normative samples that are representative of the US population when the data was collected. And with population changes over time, this is an important component of continuing to update this research, to make sure that the research that we're doing on cognitive achievement relations is representing the population of people that we're using the tests with on a regular basis. And newly developed tests also allow for further examination of different constructs in cognitive and academic domains. I won't go into a lot of depth here, but there are some new tests on the WJ5 that I think are some interesting additions. And this gives us a chance to see, like, how do those new tests function in these cognitive and achievement models? How are maybe they adding to the ability for us to predict achievement skills from cognitive skills? So we really had two big research questions for this study. The first one is, what are the cognitive achievement relations in the WJ5? So, and one thing that we did in this study was to examine both those correlated models and the integrated models of achievement, just to see how both of them worked with the new WJ5 data. And then we looked also at how do these results align with some of the previous research that we've seen. So are there some similarities that we really would have expected to see? And then also, are there some interesting differences that maybe have shown up in with this new data. So I'm going to talk about the methods that we use and kind of show some visuals just to give a good sense of what we were doing in this study. So like I said, we use the WJ5 standardization sample. And one thing that's been done in previous research and that we did here is we divided the sample up into different age groups to account for some of the developmental differences that might be occurring with cognitive achievement relations. So we know that some of these relationships tend to change over time, where some relationships get a little bit stronger and then some get a little bit weaker. So we broke the sample down into ages 6 to 9, which is sort of like kind of like late childhood, elementary, and then 10 to 14, which is sort of like early to mid adolescence, 15 to 19, which is sort of like adolescence and really kind of like high school. And then 20 to 49 is sort of young adulthood, and then 50 to 80 is older adulthood. So, so we have 5 different samples that we looked at this with. And we used what's called multi-group structural equation modeling. So what we do is we create a cognitive achievement relations model, and then we estimate the model for each of these age groups at the same time. And you'll get to see kind of what that looks like in a few slides. So hopefully that'll be a little bit more clear. We used what's called a higher order model of cognitive abilities, where we have all the broad CHC abilities at one level and then sort of like a higher level G factor above that. All the academic skills we included here were measured by 2 to 3 subtests, and then the broad cognitive abilities were measured by 2 to 4 subtests. And we categorized everything based on the broad and narrow CHC abilities, according to the WJ5 validity studies that have been included in the technical manual. So some of the information that we were able to get beforehand to make sure that we kind of knew how to categorize some of these tests. This just goes over all the different tests that we're measuring, the different broad abilities. I'm not going to go over all of them in detail, but if you've used the WJ before, a lot of these are going to look very familiar. Things like analysis, synthesis, and concept formation. But all the ones that are bold and underlined are sort of like new additions to the WJ5. Like matrices is a matrix reasoning type test, and that's new. Like that hasn't been included on the WJ5 before. There's a story comprehension test, which is sort of like a listening comprehension. In verbal analogies, if you were trained on the WJ3 way back, at least a few years ago, verbal analogies was part of the oral comprehension test that had like 3 little subtests. So that's been included now as its own subtest. So there's some interesting new additions to the WJ. And for academic skills, we looked at 3 different narrow reading skills. So basic reading, which is mostly decoding type skills. So we included letter word identification and word attack, which is reading real words and nonsense words respectively. And we also include the oral reading test on this factor too. I know sometimes people might think of this as sort of like a reading fluency test. But the reason it fits best with this basic reading skills factor is that it's scored mostly based on accuracy and not on speed. So because it's really more of an accuracy type test, the focus there really is on being able to decode the words in the test. And for reading speed, we had sentence reading fluency and word reading fluency. And then for reading comprehension, we had 2 of the tests that were on the WJ4, which is passage comprehension and reading recall. But then there's a new test called paragraph comprehension, where people or examinees read a paragraph and then they answer some questions about that paragraph. So it's a little bit more similar to maybe what you've seen on something like the Wyatt or the KTA. So that's a new test there. For math, we looked at math calculation and math problem solving. So math calculation is just solving math problems sort of out of context. And then math problem solving is more of solving problems in context. So I'm sure everybody remembers applied problems if you've used the WJ before. But there's a couple new tests that have been included. So one is math problem identification, where, if I remember right, people have to identify sort of like issues that are present in a math problem that they see. And then there's also a number sense test, which gets a little bit more at like looking at like sort of like the logic and understanding of numbers a little bit more generally. And last, we have written expression, which had, or the writing tests. So one was written expression, which has sentence writing fluency, sentence writing accuracy, which was a new test, and then written language samples, which is the same test as writing samples. It just has a new name. And for basic writing skills, we only had the editing test wasn't included in the new WJ. So the basic writing skills is really mostly a spelling factor. So we have spelling of real words and then spelling of sounds. So those are the academic skills that we included. As far as our analysis plan, I have it here listed sort of in text, and then I'm going to go through a little bit about what we actually did visually. So first, we have a model of cognitive abilities that we're estimating. Next, we add in academic skills. So we did separate analyses for the reading, math, and writing skills. Putting all of those in one model is certainly possible. I think it could be really interesting, but it was certainly probably a little more complex than what we wanted to tackle at this point. Next, we examine the cognitive achievement relations using sort of the correlated factors model, so where all the achievement factors were related to each other. And what we did is we had all the broad CHC abilities predict each of those academic skills. One thing that often happens in this research when you do that is you have some of those paths that are negative and pretty large. But what's happening there is what we call a suppressor effect. So the first thing we do is remove all of those large negative paths that are present, and those are usually present across all the age groups. And then we looked and saw like are there paths that are included that are maybe not statistically significant for any of the age groups, and then we also remove some of those. This is how a lot of the previous research had been done, so we kind of wanted to do that in sort of the same way. And then basically what we do is we estimate a final model where all the paths that were statistically significant for at least one of the age groups was included in the model. So we're not going to show you every single step we went through here. We're just going to show you that final model. And then what we did is we took that final model and we created this integrated achievement model where we had the more basic academic skills included as predictors of the more complex or the more higher order academic skills. So again, then we also looked at some of those paths that were no longer statistically significant from cognitive abilities to the complex academic skills, and we removed those. So just to give a sense of what things look like, so we started with our cognitive model here, and then we added in our academic skills here. So once we added those in, what we did is we tested whether the broad cognitive abilities are statistically significantly related to the academic skills. And here, like I only have paths from comprehension knowledge and auditory processing, but there were paths from all 8 of the broad cognitive abilities in this initial model. So for ones that were negative or not statistically significant, we removed some of those paths. So here, like in this example, like maybe the path from GA to reading speed was not significant. So then we would take that one out. So once we had a good correlated factors model, what we did is we created an integrated model. So we had all these cognitive abilities still predicting academic skills, but then we included structural paths between the academic skills. So in this case, we had basic reading skills, was a predictor of reading speed and a predictor of reading comprehension. And then reading speed was a predictor of reading comprehension. So the idea here is that your basic decoding skills, if you have really good basic decoding skills, that would likely result in faster reading skills, which could result in better reading comprehension skills. And then good decoding skills would also probably relate to good reading comprehension skills too. So here what's happening is the effects of the broad cognitive abilities on those complex academic skills might be partially or fully mediated through the basic skills. So here we're kind of looking at like the path from GC or comprehension knowledge over to reading comprehension. Here we do have a direct path, but there's also these other paths that are there too. So there's this one from comprehension knowledge to basic reading and basic reading to reading comprehension. So Danny talked earlier in the example of this. That's one of those indirect paths that we also have to consider in this model. There's also an indirect path from GC to reading speed to reading comprehension. And then there's also one from GC to basic reading to reading speed and to reading comprehension. So there's a lot to consider here when we're thinking about like what is the full effect or the total effect of GC on reading comprehension. And the idea here is that the effects of GC on these more higher level or more complex academic skills sort of work through some of the basic academic skills as well. So that's kind of what our goal was with looking at that. All right, so now that you know a little bit about what we did, I'm going to jump into the results and show you what we found. So first, I want to give just an example slide with kind of what our results looked like, just so you have a sense of what we're going to be showing. So all the results are going to be presented in tables that look like this on each of the page. You're going to see a lot of numbers, and I'm going to try to highlight some of the most important things. So each row represents the standardized path coefficient between one of the broad cognitive abilities and an academic skill. So here we've got basic reading skills, and so this is showing the effect of auditory processing on basic reading skills. And then this is also showing them across age. So each of the columns shows a different age group that we included. So this is showing the effect of GA on basic reading for ages 6 to 9, 10 to 14, 15 to 19, and so forth, kind of across development. All the numbers that are bold and underlined are ones that were statistically significant in our model, and all the ones that are italicized were not statistically significant. So even though they weren't significant for some of the age groups, we still left them in there because as long as it was significant for one age group, we left it in there for all of them. So, and then what you'll see is these red boxes will show up, and I include those in there periodically just to highlight some of the most notable things that we found. So if you're thinking, okay, I'm going to see all these numbers, what are these numbers? So these are what are called like the standardized regression paths or standardized path from the cognitive abilities to academic skills. And they can be interpreted like a correlation. So if it's a 0, that means that there's no relationship at all. If it's +1, that means that there's a perfect relationship between the cognitive ability and academic skill. If it's -1, it means that there's like a perfect negative relationship. So if it's a positive relationship, you know, is the value on one of them increases, then the value on the other one increases as well. And if it's negative, if the value on one increases, the value on the other decreases. For these, we're usually only looking at positive relationships. So rarely you're not ever going to really see like a perfect correlation between a cognitive ability and academic skill. And if you did, then they're basically kind of measuring the same thing. But we won't get into everything there. But what's most important is thinking like, how do I interpret these numbers? Usually if something is below 0.05, we're not too concerned about it. That's going to be a pretty negligible effect overall. If it's 0.05 to 0.1, that might be considered like a small effect. So maybe like a little bit of an effect, but not really big or anything. About 0.11 to 0.24 is moderate. And then if anything is above 0.25, we would consider that sort of like a large effect with this type of research. And that interpretation comes from Tim Keith in his multiple regression book. So that's kind of what you'll be seeing. And we will go ahead and jump in here. All right, so results for reading. So this table, there's a lot going on. So I'm going to start up here at the top with basic reading skills. So these are the results for basic reading skills across development and all of the 4 cognitive abilities that had significant effects on basic reading skills. So really the most notable one here was auditory processing. It was by far the strongest relationship between a cognitive ability and basic reading skills. And so there were some other effects there. So like for retrieval fluency and working memory in GC, but these were pretty small overall. So this effect was really quite large. When we look at reading speed, uh, we had comprehension knowledge, learning efficiency, retrieval fluency, and processing speed were all related. The most or the largest effect was really from processing speed, which isn't too surprising. So those reading tests that are in reading speed are timed. Processing speed tests are timed. So this isn't too surprising that those are related to each other. Um, GC was related, but this was a good example of one where it seemed like that relationship sort of decreased with age. So that background knowledge just really it's not as important once people get a little bit older. For reading comprehension, we had comprehension knowledge, fluid reasoning, auditory processing, retrieval fluency, and working memory all had statistically significant relationships. Um, the strongest relationship was definitely for comprehension knowledge, which this isn't surprising. This is something that has shown up in plenty of research in the past. So that wasn't too surprising. The next strongest one was for fluid reasoning, which we have seen this relationship with some other research as well. And then auditory processing was also had sort of like moderate relationships between or with reading comprehension here. For GR and GWM, just really quick, it seemed like that was like, especially retrieval fluency was important early on, but then kind of decreased with age. And working memory, it was kind of surprising that it really wasn't very highly related to reading comprehension, or at least not very consistently. Um, so so that was the correlated fact or the correlated model. So when we're looking at the integrated model, where we had basic reading included as a predictor of reading speed, and basic reading and reading speed were predictors of comprehension. This is kind of what we found. So again, everything for basic reading skills was basically the same or very similar in this model. Again, GA was a very strong predictor there. With reading speed, processing speed was a really strong predictor, just like it was before. That's not too surprising. Uh, and again, GC was also like sort of like a moderate predictor. It was interesting that basic reading was only a sort of like a moderate predictor for younger kids. So for the youngest group, and then sort of like that uh, preteen or early adolescence group. So it seems like for these individuals, they're probably using their decoding skills a little bit more on these reading speed tasks. But once you get older and reading becomes very automatic, you're not really probably decoding the words as much anymore. And the tasks that are included there on the reading speed, they tend to be pretty straightforward vocabulary for the most part. So we thought that was pretty interesting. Um, for reading comprehension, basic reading was a really strong predictor of reading comprehension, sort of like across the lifespan. It decreased a little bit in size as you got older, but then GC was also still a strong predictor. So comprehension knowledge still predicted reading comprehension really well, and and fluid reasoning did as well. So um, so just to get out of the table for a little bit and actually look and see like what does this look like when we're talking about the model. This is the integrated model with just for ages 6 to 9, just so you can see what it looked like there. So here we had paths from comprehension knowledge, auditory processing, retrieval fluency, and short-term working memory. Those all predicted basic reading. Um, and then I did want to point out, we also had this direct path from auditory processing to word attack, just because this is such a phonologically and phonemic based task that there really was sort of like a direct path there. Um, then for reading speed, this is kind of what we had for reading speed. So basic reading did predict reading speed for this group, but then we also have all of the cognitive abilities that predict reading speed there. And then for reading comprehension, so we just had the basic reading was a strong predictor of reading comprehension for this group. and then we had the paths from GC and GF. And you'll notice that there was no path from reading speed to reading comprehension. This wasn't really significant or very large in any of the groups. So when we're looking at this model, basic reading is an important predictor of reading comprehension, especially. It's a small to moderate predictor of reading speed, but your speed with reading, at least in this, really didn't predict reading comprehension, which was interesting. When we look at how much variability in these academic skills was accounted for by the cognitive skills and then the academic skills, it was around 60 to 65% for basic reading and reading speed, but about 90% for reading comprehension. So when we're thinking about all the cognitive abilities and these academic skills and how that explains variability in reading comprehension, we're able to explain about 90% of it with these different predictors, which is pretty remarkable. Just as a contrast, I also included the 10 to 14 age model in there, just so you can kind of see how those numbers differ. So this is just kind of going back and forth. There weren't huge differences here, but it just kind of gives a sense of what the different age groups look like. So that's what the model for reading looked like. And just got a summary of results here. I'll go through this pretty quickly because I hit on most of this quite a bit as we were going through. So, but really the biggest thing, GA was strongest predictor of basic reading at all ages. GS, or processing speed, was this large predictor of reading speed across all ages. And basic reading was a small predictor, but just for children in sort of early adolescence. And then for reading comprehension, basic reading was a really large predictor of reading comprehension. And then GC and GF were the cognitive abilities that still had direct effects on reading comprehension after including reading speed on there. So, so those are sort of like the big takeaways for reading. All right, so jumping into math. So we had math calculation skills and math problem solving. You can see that there were a lot of different abilities that predicted math calculation skills when we're looking across the lifespan. So starting there, really one of the most consistent predictors, and one that we certainly expected based on previous research, was fluid reasoning. So fluid reasoning was sort of like a moderate to large predictor of math calculation skills. And then short-term working memory was also sort of a strong to moderate predictor of math calculation skills. So these were really the two cognitive abilities that kind of had the most consistent relationships across age. And it seemed like fluid reasoning maybe increased a little bit. I don't know. It's hard to tell if there's really much of a trend there. But it seemed like working memory sort of, it started to decrease, maybe a decrease a little bit with age. A couple other things I wanted to point out here. One, that processing speed was a predictor of math calculation, but then so was retrieval fluency. And I think this was something that's interesting to think about because, recently with CHC theory, retrieval fluency kind of was separated from the GLR. So it just became GL and then GR separately. I think this kind of helps show that maybe that retrieval fluency is certainly something different from processing speed, because it was differentially predictive of math calculation skills here. So I think that that's sort of an important finding, potentially showing that GR isn't just like another type of processing speed measure. One more thing to point out here is that visual processing actually had some moderate relationships, especially sort of like in from early adolescence kind of through middle adulthood. And that's not something that we see a lot on other tests. So this was something that was not really expected to be to find on the WJ5 here. All right, so when we get to math problem solving, again, not surprising, fluid reasoning was a very strong predictor of math problem solving, really sort of across ages. And then also comprehension knowledge was a strong predictor. Those are things that we've certainly seen in previous research, and those were definitely expected. And then you can see GV So visual processing, working memory, and processing speed had some small to moderate effects at different ages, but they really weren't very consistent. Right, so with the integrated model, so here we had math calculation skills included as a predictor of math problem solving. All of these are for the most part the same. So nothing in the math calculation skills predictors changed very much. But what changed was math problem solving here. So when you include math calculation skills as a predictor of math problem solving, uh, not surprising, math calculation is a pretty strong predictor of math problem solving, and it seems like it maybe increases a little bit across the lifespan. Um, and then GF continued to be a really important predictor as well. So fluid reasoning, was important for math problem solving. And then so was comprehension knowledge. So both GF and GC were still important predictors of math problem solving after accounting for math calculation skills. So again, like I said, I like visuals, so I included a visual for math as well. And this is just showing for the ages 6 to 9, just the different cognitive abilities that predicted math calculation here. So we had comprehension knowledge, fluid reasoning, visual processing, retrieval fluency, working memory, and processing speed. So lots of different cognitive predictors of math calculation. And then math calculation predicted math problem solving. And then also so did comprehension knowledge and fluid reasoning. So that's just kind of showing what the full model looked like. And then again, I included ages 6 to 9, but then also, oh, sorry, this is just showing also the R squared. So the variance accounted for math calculation was about 60% of the variance. But then for math problem solving, all of these different predictors explained about 94% of the variability in math problem solving, which is quite a bit. And then this is just the ages 10 to 14 model, just so you can kind of see some of the contrast with the numbers between the age groups. All right, so quick summary. Again, fluid reasoning and working memory were really the most consistent predictors of math calculation skills across the lifespan. And processing speed was also kind of a consistent predictor that was small to moderate of math calculation. Then GR and GV were a little bit more inconsistent across the lifespan. But when we look at math problem solving, math calculation was a very strong predictor of math problem solving, and it seemed to increase in size with age. And then both GF and GC continued to be good predictors of math problem solving as well. So fluid reasoning, comprehension knowledge, they were both they both also predicted math problem solving. So all right, so getting into the last part here, talking about writing. So again, we had our basic writing skills was really more just spelling skills. And we had comprehension knowledge, auditory processing, retrieval fluency, and processing speed that were predictors there. So kind of like basic reading skills, auditory processing was a really, really strong predictor of spelling skills. And it was just by far the strongest predictor of all the different cognitive abilities there. So that auditory processing, phonological skills was really, really strongly related to spelling skills. And this was true sort of across the lifespan. GC was related. It was a little bit more moderate and only with older ages. And then we see both retrieval fluency was important sort of early on, and then processing speed had important relations sort of in older ages, but these are pretty small to moderate for the most part. So for written expression, again, this was pretty interesting that GA, so auditory processing, had a pretty strong relationship with written expression here as well. And so did fluid reasoning. So that was one of the other most consistent and strongest predictors was fluid reasoning for written expression. Here again, retrieval fluency had a strong predictor, was a strong predictor early on, tended to decrease a little bit with age. So then when we look at the integrated model, where spelling was included as a predictor of written expression, All the spelling results are pretty much the same or very similar to the last slide. And with written expression, not too surprising, spelling was a really strong predictor of written expression. So again, the basic academic skills is a strong predictor of the more complex academic skill. Fluid reasoning continued to be an important predictor here as well of written expression. And you can, if you remember on the other slide, these paths from GA to written expression were really pretty large. They were like around 0.5, 0.6. They're a lot smaller now, but that's because some of those effects are being mediated through this path from GA to spelling and then spelling to written expression. So you'll see that on the next slide. But retrieval fluency continued to be sort of a moderate to small predictor, and then GA, as far as the direct path, was sort of like moderate to large, but just for some age groups. All right, so if we're looking at what the model looked like, this is the age 6 to 9. So here we had auditory processing that was a really strong predictor of spelling, and then retrieval fluency that was also a good predictor of spelling. And then we included written expression in there as well. And so you can see there's a very large path from spelling to written expression, but then there were also paths from fluid reasoning and retrieval fluency that were significant to written expression. And as far as variance accounted for, about 65% of the variance in spelling was accounted for by the cognitive abilities, and then it was about 93% in written expression that was accounted for by the cognitive abilities and by spelling. So, so very similar to sort of like the reading and math models where these complex academic skills were explaining a lot of the variability in those skills by including both cognitive and achievement predictors of those skills. And then I also included just the age 10 to 14 model as well. So just to kind of see the contrast between the two age groups. All right. So summary of those results. Again, GA was a really large predictor of spelling. It was also a very large predictor of written expression. And then GC was sort of a moderate predictor of spelling, and then GR and GS, so retrieval fluency, processing speed, they were kind of inconsistent. They were moderate for some ages. And it seemed like that retrieval fluency was maybe a little bit more important for children, but less for adolescents or adults. So with written expression, again, spelling was the strongest predictor of written expression, but then fluid reasoning was also sort of moderate to strong. And then retrieval fluency and auditory processing were both sort of like small to large predictors. GR, that retrieval fluency seemed to decrease a little bit in size, and as people got older. So, so now you've seen all those sort of like direct effects from broad abilities to academic skills. So one thing that a lot of times we do in this research, especially if we include G in our model, like general intelligence, we want to kind of know how much of those effects of G or general intelligence are also sort of related to the academic skills. So in the models that we looked at here, that general intelligence path, there's no path that goes from our G factor to any of the academic skills. Usually if you include those paths are negative and large. And basically the way we kind of think about it is that the influence of general intelligence kind of works through those broad cognitive abilities. So one of the things that we can do, though, is we can estimate what the indirect effect of general intelligence, or G, is on all those academic skills. So you have to do all kinds of multiplication of different paths, like the paths from G to the broad ability, and then the path from the broad ability to the academic skill, add them all together. I have an example of what that looks like here for looking at the effect of G on basic reading skills. You got to do all this multiplication, add them all up, and you get something at the end. Luckily, M plus, what I use to estimate all these models, will do all this for me. So all I have to do is ask it to provide all these indirect effects. So I didn't have to go through and calculate all these, thankfully. And then, so the other thing that we did is we sort of took that variance accounted for to give an estimate of the proportion of variability in academic skills that's that could be explained by whatever general intelligence is, but then also the broad CHC abilities too. So again, you're going to see some tables with a lot of numbers. But first, I just kind of wanted to show just a little bit of what this looks like as far as what we're doing as far as separating these effects. So if we're just looking at basic reading up here, and we want to know the effects of general intelligence on basic reading, we're taking each of these paths, so the path from general intelligence to working memory, and then working memory to basic reading, and we're multiplying those together. Then we're going to multiply the one from G to GR, and then GR to basic reading skills, GA or G to GA, then GA to basic reading skills, G to GC, GC to basic reading skills. So that's how we calculate that indirect effect. When we're looking at something like reading comprehension, this one is much more complicated because there's this path from basic reading skills to reading comprehension. So the only paths that go from general intelligence to a broad cognitive ability to reading comprehension are GC and GF. But then we have all these other paths here that go through basic reading skills. So we have to calculate those ones, but then also calculate from G to working memory to basic reading to reading comprehension, from G to retrieval fluency to basic reading, reading comprehension, and so forth. So basically what it's saying is that there's a whole lot of little multiplication and addition that goes on behind the scenes here, but that's the basic idea of how we do that. So again, there's some tables with a whole bunch of numbers here, but I'm going to talk a little bit about what's going on. So first, I wanted to kind of show a little bit on this R squared. So this is the how much variability in academic skills is accounted for by all of the predictors in our model. So including both cognitive abilities and academic skills for those integrated models. So with the more basic academic skills, so like basic reading, math calculation, and spelling, that tended to be sort of between about 55 and 65 to 70%. So for the basic reading skill, or for the basic skills, it was like a decent amount of variance that's accounted for, but there's still a decent amount also left over. That means that there's about 30 to 40% of variability that we don't know what explains that. For the more higher order skills, we were getting numbers that were close to like around 90, between 80 and 90 and above 90 at times. So the cognitive abilities and academic predictors of the more complex academic skills, we're explaining a lot of the variability in there by including both of those predictors. So if we are looking at this idea of the indirect effects of general intelligence on each academic skill, these effects are pretty big. They were all, for the basic academic skills, they were all sort of around 0.7, 0.75, somewhere in that range. And then for the more complex or higher order academic skills, they were all sort of around 0.8. So if we're only looking at G as a predictor of academic skills, if we just wanted one thing that predicted it, general intelligence would do a really nice job based on this model. If we're looking at broad abilities, and what I did here is I just kind of looked at the total combined effects of all the broad cognitive abilities. If we were able to kind of take all those and see what is sort of the unique effects of all the broad abilities on each of the academic skills, we're getting effects that are around like probably between about 0.2 and 0.4, which are overall, those are decent sized effects. They're certainly smaller than what you would account for by general intelligence. And then for the more complex academic skills, they tended to be more like around 0.4 to around 0.5, maybe like a little bit higher than 0.5. So basically what this is saying is that even though general intelligence has big effects on the academic skills, the broad abilities kind of together they're also explaining a lot of variability in academic skills too. So that's kind of what this is trying to show. Like if we look at how much of the variance, or kind of like the proportion of variance explained in each academic skill by broad abilities, for those basic skills, it's sort of around 10 to about 26% or so. And for the more complex or higher order academic skills, it's more like around 20 up to around 30. When we look at that for general intelligence, though, it's general intelligence does explain a lot of that variance for basic skills, and it also does for some of the more complex skills too. So this is just trying to like pull those influences apart. I know there's a lot of numbers on these different slides, but hopefully that kind of shows a little bit of what's going on there. I think one thing that's important to think about with this is really trying to interpret what these mean and and what they mean as far as cognitive achievement relations. So like one question that we can ask here is just like, well, what is general intelligence? Um, so really we can think about it is that it's representing all the variability that's shared amongst broad abilities. I don't know if anybody went to some of the other talks today, but Conway and Kovacs, they were talking a little bit about process overlap theory, and that the kind of the differences in interpretation of general intelligence as this separate ability versus something that's more like a statistical artifact. Um, and that's kind of what I talk about in this middle thing here. It's like, so maybe G is some separate independent ability that explains why the broad abilities are correlated together. Um, but it could be something that's just more like a statistical artifact. So it comes up because we're using similar methods to obtain test scores. So all of these tests are individually administered versus group administered using tests versus rating scales or observations. So there's these sort of methodological um, issues that can be related. Um, and then sort of related to the process overlap theory, this third bullet is it could be like a statistical artifact that arises because the cognitive processes, more the basic processes that you need to understand and respond to test items are shared among all the different tasks. Like you need to have some level of attention in order to do any of the tasks on an intelligence test. Just your general speed of cognition, your language skills, just basic perceptual skills. So there's a lot of things that are shared among all the tasks. And that could be one reason why there's this thing called general intelligence. So I think sort of the takeaway here, I don't have the answer to what G is. Unfortunately, I know I'm sure everybody was hoping for that today, but that's not an answer that I've got. But really what's important is that the variability that's shared among all those broad abilities that creates general intelligence is also shared among all those academic skills. And the broad abilities may account for a smaller proportion of that variability in academic skills compared to whatever general intelligence is, but it's still substantial. It's not something that we necessarily should completely ignore. It is providing something that is unique to our understanding. And I think with that, that is the end of my part. So that was a lot of talking. And Danny, I'm going to have you take over from here to talk about implications, limitations, and future directions.
Okay, hello again, everyone, and thank you for sticking with us. I know we're right at about 30 minutes to the end of our session on a late afternoon on Friday, so thank you. And I know we presented quite a few numbers in regards to these different relationships, but what's really exciting about this research is it's really the first of its kind with the WJ5 really informing the science of cognitive achievement relations. And some of the next, this kind of final piece we're going to present to you are, after all this, you've seen these integrated different analyses, what can you take to the bank in terms of helping to inform practice? And so let me jump to this first slide here. In terms of just a quick broad overview. So like what are really, I would say, more the practical implications of these kind of empirical findings? And we have some implications in terms of what we found with the predictors of academic skills. And then we also have some kind of practical implications in terms of assessment considerations. So, and these are just broadly speaking. So the first is when we look at our findings, we found that different cognitive abilities were important across different academic skills. So what was important in terms of cognitivity predictors of writing, may have not been as important for mathematics or reading. We did see some similarities between reading and writing, again, because of some of that overlap there. But one of the things we saw across all these academic skills is that comprehension knowledge, GC, tends to be one of those important broad abilities. Another kind of big overall finding we found is that intermediate academic skills were also an important predictor of those advanced academic skills. So again, not only were the broad cognitive abilities important explanatory variables of reading, writing, and math, but we also found that basic reading and reading speed were important contributors to reading comprehension. We found that math calculation was an important predictor of math problem solving. And then finally, we found that spelling in particular was a really strong predictor of written expression. And so I think that's another kind of key point there. In terms of broad assessment considerations, there definitely were shifts observed in terms of the importance where the size of the effects for cognitive abilities and intermediate academic skills differed across development. So that's a mouthful. So basically what we found is evidence of moderation based on developmental age. So we found that, for example, GC may have become more important. Some of those kind of intermediate academic skills may have become less important over time, right? So it's important to kind of think about that. There is a shift in the importance of both cognitive abilities and those intermediate academic skills in explaining the complex academic skills, depending on where we were at in terms of development. And then lastly, what's really cool about these integrated models, and I think the visuals just really kind of help visualize, kind of what we were doing. But there's a lot of different variables in the model. When we look at the WJ in terms of the number of broad cognitive abilities, when we include the intermediate academic skills and the complex academic skills, there's multiple of those. So what our findings show is that basically, depending on what the academic skill deficit is, that is what should drive our focus of assessment and interpretation. And what that should be is on those most important cognitive abilities or academic skills. So just as a kind of a quick example, I can't quite recall exactly what the model looked like, but whatever were the most important predictors of reading comprehension, right? If we were to have a reading comprehension referral, then we should focus on what those predictors were in our model, because that'll help us narrow down in terms of where we should really focus our attention, where we should focus our interpretation, and kind of drill down there. So that's just kind of another important assessment consideration. Okay, in terms of kind of what you can take to the bank, one of the courses I teach at Texas A&M is cognitive assessment. And I know that's one of those courses that a lot of faculty like to kind of steer away from. But it's one of the classes that I really love to teach. And, with the WJ5 that's going to be coming out very soon, this slide here is one that I would hang on to in terms of what we found on the WJ5 and also how it was consistent with past research. So let's just kind of go through these. The first, in terms of what was a finding that was similar to past research, auditory processing was indeed the strongest predictor of basic reading skills and spelling. And if we just kind of think about that in terms of auditory processing, really being a measure of those kind of basic and advanced phonemic awareness skills, measuring that kind of phonological processing piece, that's really implicated in sounding out letters, sounding out and decoding words. And also when we think about spelling in terms of trying to piece those letters together based on those phonemes, it makes sense that GA was one of the strongest predictors of both of those. Consequently, as a side note, when we think about like dyslexia, it's often why we see auditory processing or phonological processing as often implicated in explaining some of the difficulties that we see with basic reading and spelling. Is just kind of a side note. Another kind of key finding that was similar to past research is that basic reading skills was a large predictor in terms on the scale of the effect sizes. It was considered a large predictor of reading comprehension. But one important nuance is that the effect of basic reading skills on reading comprehension, it tended to decrease with age. So that's an important piece. In the study that I did back in 2014 with the KBC, we found the exact same pattern. Basic reading skills was really important for reading comprehension, but that effect decreased with age. And instead, what we saw is that GC became more important over time. Again, that makes sense as reading comprehension becomes more demanding. It requires higher order cognitive processes and less so on the basic reading skills as those become automatic. So this finding really makes sense and is consistent with previous research. Again, another consistent finding that has been often replicated is that comprehension knowledge, or GC, it was the strongest cognitive predictor of reading comprehension. Again, that makes sense when we think about the linguistic demands of reading comprehension that's required. And when we think about GC being that kind of measure of language development, of lexical knowledge, of background knowledge, when we're actively reading a text, we're calling on our background knowledge and how it relates to what we're reading. So it again, that was very consistent with past research. In terms of fluid reasoning, just those kind of inductive and deductive kind of reasoning skills, those reasoning powers, they were certainly a strong predictor of both math calculation, math problem solving. Again, that's consistent with previous research. In terms of looking at math calculation skills, it was the strongest predictor. So while fluid reasoning was a strong predictor of both math calc and math problem solving, math calculation skills was actually the strongest predictor of math problem solving. And in fact, that effect tended to increase with age. Again, that is similar to what we found in the KBC2, which we published in 2019. And if we just unpack that just briefly, I always like to say this, mathematics is a little different in terms of reading, whereas, once a child learns to read, they just read to continue just to learn information, right? Once they have the reading down, it jumped ahead. No, not yet. Okay, coming back to this. So when reading, at first we learn to read, but after that we just read to learn information. The difference is with mathematics is you're constantly learning new skill sets as you advance in grades. You're learning new equations, new algorithms, how to set up new and different complex problems. So you're constantly having to lean on those prior math calculation skills. And that's especially the case as you advance in grade level. That's why we saw not only math calculation skills being the strongest predictor of math problem solving, but that effect actually increased with age. So that is a very kind of consistent finding, both with kind of what we know about theory of it, as well as just empirical knowledge. And another common finding that we have often seen is that comprehension knowledge, it was a moderate predictor on the effect size scale. It was a moderate predictor of math problem solving, and that tended to decrease with age. Again, we often see GC being a significant and often moderate predictor of math problem solving, in part because of the language overlap, math problem solving and involving kind of those word problems. Even some of the reasoning involves is mediated by language, and that's exactly what GC is tapping into. So we see that relationship. And then last, a finding that really overlaps with previous research is that fluid reasoning, those reasoning powers were really found to be either a moderate to strong predictor of written expression, but that has been a little less consistent in past research. It kind of really depends on what I kind of think depends on the test battery you're using and how written expression is being measured. But we do see some relationship there with fluid reasoning in terms of putting together a written prose. Again, so to me, this is one of those kind of key takeaway slides when you kind of boil it all down and distill it. This is something that, I would want to take into the classroom or practice in terms of understanding the science of cog-achieve relations as it exists on the WJ5. So we documented similarities with previous research, but there were certainly some differences, and some of these are actually pretty interesting. So the first here, and Chris talked a little bit about auditory processing here, but auditory processing was indeed the largest predictor of basic reading skills across all ages. Wasn't surprising given some of the skills involved, but in past research, it's typically either been comprehension knowledge, short-term working memory, or even processing speed or some combination. But in the WJ5, again, we found auditory processing was the largest predictor of basic reading skills. And we included this note here as to kind of explain why that might be. So on the WJ5, in terms of how GA is measured on the WJ5, they have included some more phonologically based tasks. So in terms of being able to blend phonemes, right, to kind of say the word or segment the phonemes in a word. They also included some tasks where you're deleting a phoneme and then having to say that word, or even substituting a phoneme for a different one, so kind of changing that word. So it had some more kind of phonologically demanding task components to it, which is why we think it was probably one of the reasons why it was the largest predictor of basic reading skills. It kind of better mapped on in that way. But that wasn't always consistent with past research. Another finding on the WJ5 that was a little different than past research is that fluid reasoning was found to be generally the strongest predictor of math calculation skills. And this was regardless of kind of developmental age level. However, short-term working memory was still large. In a lot of the past research, we found short-term working memory to kind of be one of the main drivers. Here, it wasn't the case, it was fluid reasoning, but GWM was still important. Why do we think that might be? Again, on the WJ5, in terms of fluid reasoning, it did include a new test called matrices. And that test does include an aspect of inductive reasoning, which is a broader representation of fluid reasoning of the factor. So again, a little bit more similarity in terms of the mapping. Okay, two other differences that we found on the WJ5 that are different from past research. This one was a little somewhat surprising. Comprehension knowledge, or GC, it did not predict written expression, and instead it operated totally indirectly through spelling. So again, the effect of GC on written expression, it only occurred indirectly through its effect on spelling, and then spelling predicted written expression. So again, this integrated model approach, which you saw several kind of visual depictions of, it really may be the primary reason for this difference. And it really highlights the importance of kind of considering these foundational academic skills that kind of give rise to the more advanced academic skills. And then lastly, something that we've kind of been driving home throughout, and you've seen in the models, is that these intermediate academic skills, what we typically think of is like basic reading skills, reading fluency, math calculation, or even spelling. All of those intermediate academic skills played a real prominent role in predicting kind of their respective advanced academic skills like reading comprehension, math problem solving, and written expression. And so more research on these kind of integrated models is needed to kind of continue to refine our understanding of how they kind of impact our understanding of cognitive achievement relations. But one of the things I immediately think of in terms of a practical consideration, if I have a referral, for a concern for a more advanced academic skill, not only am I wanting to assess those kind of relevant cognitive abilities, but also those kind of intermediate academic skills and how they may kind of be contributing or playing a role to that advanced academic skill. I think that's one important implication there. Okay, in terms of limitations, in terms of this study, so the relationships that we showed you today, they really represent the average relations between cognitive abilities and academic achievement. Chris and I actually gave a Cog Achieve presentation yesterday, and what we did differently there is we kind of looked at how do Cog Achieve relations on the WJ5 differ according to ability level or IQ level. And we did find differences according to IQ level, and then Chris and I published this paper in 2023 where we looked at differences in cognitive achievement relations on the WJ3 and the WJ4, and we also found differences there. As just kind of a quick plug, and I'm just kind of generally speaking here, we tended to find that general intelligence had stronger influences on academic skills at the lower end of the IQ continuum, whereas kind of the broad or specific abilities tended to have stronger influences on academic skills at the average to higher end. Okay, and so just some kind of interesting findings there that also speak to maybe we should be looking at that dimension as well. But certainly that's a potential limitation here because we didn't look at that. But we certainly need more research to understand cognitive achievement relations for individuals with a specific learning disability. The relationships certainly may be different and could be informative for understanding these relations within that population. As a side note, we've also looked at in a study that we published, I believe in 2020, we looked at how cognitive abilities influence academic skills for those who are at the 10th percentile of that academic skill versus them being at the 90th percentile of that academic skill. And what we find is that cognitive abilities in some instances had stronger influences on the academic skill when it was at the 10th percentile. And kind of the reason that matters when I'm thinking about school psychologists, special educators, anyone in this psychologist, anyone in a support role doing these evaluations, we're typically getting referrals for kiddos who may be represented more at the margins, at the 10th percentile of achievement or lower. And so how cognitive abilities influence academic performance on that lower end is also an important consideration that we should continue to think about and refine. Some other limitations, the WJ5, it's exciting, it's a new test battery, but at this time, there's still not been a significant amount of research on the new test. Certainly excited about the opportunity to do that here. But we do need to continue to work on our understanding of what the new tests measure. And some subtests that are new were not included in this analysis. So just another limitation there in terms of future research, we may work to kind of include all of those tests. In terms of future directions, again, we do want to continue to refine our understanding of cognitive achievement relations through further analysis. And this may look at different things like including more subtests like we just mentioned. It can include, conducting more of those kind of meta-structure equation models that Pong Pong and others have done. We're also certainly taking that kind of more integrated approach where we're looking not only at cognitive abilities, as well as foundational academic skills and how they predict those more advanced academic skills. And then as well as thinking about how do these cognitive achievement relations kind of differ by IQ level? We know there's some evidence out there that it does differ, and that's been found on the WJ3, 4, and WISC-5. So, that's and the WJ5 as well. So that's something that we kind of want to continue just to kind of unpack and look at. Something else that hasn't gotten enough attention is we need to take a closer examination of how those kind of narrow CHC abilities, how they predict narrow academic skills. One way to achieve that goal is to be able to have better construct representation of those different CHC constructs. And the way to do that is really have more tests. So that's kind of one way to get around that issue and to be able to address that. Another future direction is really just looking at different moderators of cognitive achievement relations. So I'd already kind of talked about this up above, but really looking at, we know cognitive abilities are important predictors of both intermediate academic skills and advanced academic skills, but let's look at different moderators in terms of what influences that relationship. We know that general ability level or like IQ level does. We certainly know that age or developmental level does. For example, we saw that like GC becomes increasingly important in predicting reading comprehension, whereas basic reading becomes less important in predicting reading comprehension. That's just kind of one quick example of evidence of developmental level or age moderation. But also, we're really focused on the group of specific learning disabilities. So we may want to look at how SLD status versus not SLD status may affect cognitive relations as well. And then last, again, mentioned this, kind of sprinkled it throughout, but in terms of looking at the meta-analysis of cognitive achievement relations, we really think that that is a kind of an avant-garde approach to really aggressively advancing the science of cognitive achievement relations research. And the benefit of that type of work, again, is instead of just looking at one battery, we can look at 50 batteries simultaneously, all integrated. The challenge there is just kind of aggregating all the data in a nice way. But when we can measure cognitive relations across many different batteries simultaneously, we can really increase our reliability of those estimates in a way that we otherwise couldn't with just a single battery. And perhaps Chris can speak a little bit about this, towards the end, but I know he's really been working on the analysis piece of our meta SCM, but we've been working on building that database, gosh, I don't know, maybe close to 2 years. And I think we presented on this last year, and it's a monstrous number of data sets, but it's exciting work that I think is going to advance the science of this work. Okay, so a lot of information today. What's kind of the takeaway message? Just a kind of few points to wrap up. Number one, cognitive achievement relations with the WJ are fairly consistent with previous research. So that's that is a comforting finding to find. And that tells us that, okay, a lot of these construct relations are not test specific. They actually generalize across different test batteries. So that's one kind of key important finding. Another takeaway message is that really the examination of integrated models is really the route we need to go, and it's really helpful for understanding how basic academic skills predict higher order academic skills. And that really just better maps onto reality and how this kind of academic skill development really works. And so our model should more and more model it that way. A third takeaway message is that the updated WJ5 tests, they do provide some interesting and new insights into the prediction of academic skills, including some of the changes kind of to the GA tasks, and to some of the other tasks we mentioned, like GF, including matrices and whatnot. So there's kind of some interesting and exciting developments there. And I'm also excited about the reading comprehension measure, including kind of that paragraph comprehension subtest. So some of those kind of innovative changes are exciting that we look forward to putting into practice. And then last, we do need to just continue to examine those integrated models of achievement and cognitive abilities, really to better understand what we call this potential cascade effects across development. And what we mean by that is, cognitive abilities influence the development of other cognitive abilities, which influence the development of academic skills, which further influence the development of those kind of more advanced academic skills. So it's kind of this cascading developmental effect, and we really want to model that as closely as possible. Let's see where we're at here. Okay, so again, just want to thank you for your time and open up for any questions or comments.
Thank you, both of you. That was wonderful. We have a series of questions that people would like to answer, so I'm going to get right to them, and I will allow you to decide who would like to address which one. So I'm going to go back, starting with Elizabeth. Elizabeth Hayashi asked if there is any reason rapid naming and orthographic processing were not considered for reading fluency.
We're not considered as far as we're not included in the model,
I'm thinking that,
or that weren't predictors. But I'm gonna go back really quickly here.
Elizabeth, if you want to clarify, you can type in the chat and I'll pass it on to them. But I think that's what she may have been asking, is that were they not a part of it? And I'm wondering if it meant merely that you didn't have the data for that.
Yeah, for orthographic processing, I would say that that's one of those abilities that I think at this point is not well represented, is like a clear measure of just like orthographic processing on something like the WJ at this point. A lot of people will look at it, they'll look at like spelling as sort of like an orthographic processing type measure. But there's obviously other things that go into that. So we did have retrieval fluency. So does have rapid naming tests that are a part of that. So there's rapid number naming, rapid letter naming, phonemic word retrieval, and then semantic retrieval, which those are more like this is coming up with words that start with specific phonemes. And then semantic retrieval is the same as the retrieval fluency test on the other versions of the WJ, where you're coming up with like as many animals as you can in a minute. So this is measuring that ability that we call like retrieval fluency that includes rapid naming pretty broadly. And that was related to basic reading, and it was related to reading speed. I'm going to go back to the table. But GR was only related to reading speed later on, which is actually kind of interesting.
Yeah.
So for older adults, that's when that component with rapid naming became more significant. For basic reading skills, it was that retrieval fluency was a little bit more important early on. And Danny, I'm going to take you away from controlling the screen. A second. There. Stop remote control. There we go. So hopefully that answers that question a little bit. So So we had tests of rapid naming in here, but they were a part of this more like general retrieval fluency factor.
Mhm. We're getting comments here. People are wanting more of this kind of research, but they want more of the subtests to be included. For example, I'll read, Jim, I'm going to read your question here. He says, first comment, exceptional, incredibly valuable presentation. Thank you. He says this research will help with designing school district PSW models and when explaining assessment results to teachers, parents, and students. For example, why is this academic task tough for you when other tasks are easy? He's hoping that the new WJ Achievement Number Concepts cluster might be included in the research area of number sense, right? Just as you use the WJ Achievement Auditory Processing. And Elizabeth was following up with that, where she's saying, orthographic processing is part of the dyslexia diagnosis. So she wants to see more research in that brought into it as well. So, as Jim said, he's so impatient, but, you can only work with the data that you were given. I understand that, right?
Yeah, and the one thing that becomes hard is there's a lot of tests and they measure a lot of different things.
Mhm.
Um, but when you include like everything in this model, like it gets really messy because there's some tests that sort of measure a mixture of things too. Like one is nonsense word repetition. So that is something that's included on the WJ5, but it's really sort of a mixture of auditory processing and working memory. And when you just get like a lot of those sort of cross loadings and things like that, that the model just gets very messy. So we were trying to do something that was sort of like a middle ground. We didn't want like only the two tests that measure the
Mm.
broad abilities. We wanted to expand it a little bit, but we didn't go and put, everything in here. And just really quick, I will completely agree with the orthographic processing. I think that that's something that we really need to understand better, and to measure better, because I feel like we do a great job with the phonological piece. Um, but I think doing a better job with that orthographic piece would be really helpful, um, and especially from the dyslexia side.
Mhm. All right. Don Torpy asks, I'm interested in the relationship between reading and fluid reasoning. I always thought there was more, they were more I'm sorry, that fluid reasoning was more related to math. I'm losing my ability to read here. So I guess she's commenting on the lack of stronger relationship between GF and reading.
Yeah. And really the main place where it was related, and I assume you can still see my screen here, right?
Yes.
Um, was here with reading comprehension.
Mhm.
So there was a small relationship. It's not really large. And I think it's because our reading comprehension tasks sort of measure a mixture of things. If if they had a lot of like inferential type questions, like if you read a paragraph and then you have to sort of really go beyond what the paragraph says
Mhm.
or what's being asked and kind of use your reasoning skills to answer it, then I think there would probably be a stronger relationship there. But some of these, like reading recall, is very much like I'm going to read it and I just need to tell it back to you.
Mhm.
Whether I can kind of infer beyond that, that tester isn't measuring that as much. So, so there is a small to moderate relationship, but really the background knowledge and in this case your basic reading skills too were the kind of the best predictors there of reading comprehension.
Exactly. All right, understood. Shireen Allison asks if you could speak a bit more as to the evidence that your study provides regarding how GS processing speed and GR retrieval fluency are actually distinct.
Yeah, that is something I would actually like to look into that a little bit more. Um, but that is something that showed up in a couple areas. So, like this was one example here where retrieval fluency was not a really strong predictor of reading speed early on, but it became a little bit stronger with age. Whereas like processing speed was sort of like a strong predictor across age. what's important about all these effects is that, this effect from retrieval fluency on reading speed this is an independent effect, like apart from processing speed here. So all of these effects it's kind of like, this is the effect of retrieval fluency after controlling for effects of comprehension knowledge, learning efficiency, processing speed, and basic reading skills. So these are like independent effects. I think this is something that it would be good to do some more work to really try to differentiate it a little bit more, and get a better understanding of why they're distinct and how they're distinct. But I thought there was at least some preliminary evidence here that really kind of shows that, yeah, these do seem like they're separate abilities.
Mhm.
Dawn also asked a question. Dawn, you might need to help me clarify here a little bit. Research from a presentation yesterday regarding IQ and age seems to make it even more difficult, although I'm wondering if Dawn, if you're referring to difficult in terms of determining a learning disability when forced to use the discrepancy model. And she asks any thoughts about how to get around that. So yeah, she's kind of saying, gee, what you're showing seems like it might make it even more difficult to be able to find a discrepancy, especially using a discrepancy model. Whether you had any recommendations about what might be done.
Yeah. I, I don't know if she might be talking about our presentation from yesterday, where we showed some of the differences across age,
Yes.
as far as relationships. Yeah. Um, I think I think that's one of the things that makes the discrepancy model just one that if you can avoid using it, I'd probably just not use it. I know that that's not easy to do when you're working for a district that requires it, or sometimes some states even still require it. Um, but I think there's more nuance there than is in the discrepancy model. Um, because, what we were seeing is that there were sort of like differences in the relationship between, especially like a full scale, like a general intelligence and academic skills across age. And if there's a difference in that correlation, then that changes also sort of the discrepancy between those skills that you would expect to see if somebody was going to meet like a discrepancy criterion. Um, so I think her comment is correct that it is more difficult because I think that that's more nuanced than what a lot of the discrepancy models and procedures that are out there. Um, they don't account for those things at this point. Um,
Mhm.
so I think that the answer there is yes, it does make it more difficult. Um, and I think we could try to figure it out and see like for a specific battery, like what how does that change? So like with age, and with somebody at a certain IQ level, what would that discrepancy need to look like, based on what we know? So, but that's like maybe like two or three steps beyond sort of where we might be at this point.
All right. Well, I'm going to wrap things up with my question because I have one final question. Jim, I don't know if I'll get to yours, but I got to ask this because I was struck by, Dan, what you were saying at the very end here. Could it be that GC doesn't predict written expression very well? Possibly because most written expression tasks tend to emphasize the actual production of writing, that is handwriting, much more than they do the ability to express your thoughts, which need to be put down on paper. So if an examinee could use, for example, a keyboard or some type of speech to text platform, do you think then that GC would actually have a better relationship to written expression?
Mhm. That's a great question. My initial thought to your question is yes, I do think it might, because I think a lot of the writing task is often placing a demand on the examinee to figure out how to produce the actual spelling pattern of a word, right? So calling forth how do these kind of phonemes and graphemes link together, string together, and I'm going to write these words down. And that can become more of the focus rather than producing kind of a more coherent global kind of written text. I also think, though, another aspect is that, the writing tests across some of the different achievement tests tend to differ as well in terms of the demands that it requires. So I think that could be a factor in terms of determining how much of an effect GC has versus spelling. So I think that's another variable at play there. But I do think you're right. I think if you put less onus on how to figure out how to spell the words and where they could just do kind of voice to text, I think you may see GC play a larger role.
Thank you. All right. Jim's final question, and this is it. He asked, are rapid automatic naming and GR the same thing, other than the method of response, oral versus written?
Well, so rapid automatic naming is those are some tasks that are included in this ability of retrieval fluency. And I don't think there's no writing involved in any of these. So I think so GR here is it's a little bit broader than just rapid automatic naming as far as like rapid letter naming, rapid number naming. It's also measuring sort of like more like free retrieval as well, as far as different categories of like animals or games or words that start with a specific letter sound. So in this study, what we were doing, this is a little bit broader. But what we could do though is we could look at a model that only includes rapid naming. Like, so we could look at this really as a much more specific rapid naming type factor too. So that is another way that we could examine this. And maybe we will once we start to put this together for hopefully a paper sometime very soon.
Jim says that would be cool. All right, we're over 5 minutes here, so I just want to say thank you personally for sharing your expertise, lending your time to the conference. We really very much appreciate it. I know that all of the participants who are here also appreciate it, and we really enjoyed the presentation. I have learned a lot, much like I did last year, so thank you very much for that. It's been great having you, and thank you for completing the conference for us in this nice manner. So Dan, Chris, thank you very much. I really applaud your efforts and am very grateful for what you've done.
All right. Thank you very much.
Thank you, everybody.
Yeah,
Bye,
thank you for being
everyone.
here.
Thank you for participating. Hope to see you all next year. And Chris and Dan, we may have you back again with these new analyses that we just recommended, right?
That's right.
Thank you, everyone.
Thank you.
Thank you.